What is a paradigm? Excellent question. When we talk about a paradigm, we mean a scientific paradigm in the sense that Thomas Kuhn used it. A paradigm exists in a scientific community, and it expresses itself in terms of things that the scientific community agrees on. A scientific community that shares a paradigm agrees on certain important things. They will agree on how to use and understand certain concepts, such as mass, orbit, perigee, evolution. They will agree on certain problems that they're interested in solving. But maybe most importantly, they will agree on certain exemplars. These are examples of excellent scientific practice, things that they can show to other scientists and learn from in order to demonstrate how you ought to go about doing your scientific research or solving your scientific problems. It's really these exemplars that the word paradigm comes from. Kuhn mostly thought of paradigms as being these examples, these paradigmatic cases of excellent scientific work that form a foundation for the whole field as other scientists strive to imitate them. The creation of a paradigm is itself a major accomplishment. Getting agreement on the fundamentals of how to do science and what sort of objects science investigates is tricky. Before you develop that consensus, you are in the pre-paradigm period. One of the things to recognize about these paradigms is that they're discipline-specific. You can have a working paradigm in one area of science and be in a pre-paradigm period in another one. An example of a scientific field where it arguably took a bit longer to create a genuine paradigm might be chemistry. The scientific revolution that took place in the 16th and 17th centuries was mostly a revolution in astronomy and physics. Chemistry and biology would take much longer to come into something more resembling their modern forms. A lot of the 17th century chemists were still quite literally trying to turn lead into gold. Once you have developed some exemplars and you've gained community consensus on concepts and problems, then you have a new paradigm. You have normal science. In normal science, you have well-developed and agreed on methods to solve problems that everyone accepts as problems. A lot of contemporary scientific research fits very neatly into this pattern, where you have labs that have research funding to approach a problem using methods and techniques that are well understood and known to be effective. Over time, however, trouble brews. Scientists become discontent. They look at the problems that they're faced with, and they begin to doubt whether the paradigm they're using has the resources to really solve. Then they start to question foundational concepts. They begin to stray from accepted ways of doing things. They become rebels, revolutionaries even. And that's when we enter the period of revolutionary science. Revolutionary science has some things in common with the pre-paradigm period. There's no consensus on what the concepts, problems, or exemplars are. But by throwing out all that old baggage, the new paradigm can potentially solve these old problems that were giving the scientists trouble. The first paradigm we're going to look at is Aristotelianism. Aristotle was so important. He covered so many different topics. And the work that he did on logic, on biology, on chemistry, on astronomy, on physics, on metaphysics became foundational for the way that the natural philosophers of the classical world understood nature. Aristotle wrote about everything, and so much of what he wrote ended up being incredibly influential. Because Aristotle wrote so much, we are not going to cover even a small fraction of it in this video. If you're interested, this is one of those areas where doing some supplemental research of your own could be helpful, and your textbook has some things that are on this too. I'm going to talk in this video about just two aspects of Aristotle's natural science, his account of motion and his understanding of the cosmos. That's because these will dovetail very nicely into our next scientific revolution, the scientific revolution. For Aristotle, there were two kinds of motion, natural and violent. Natural motion was an element trying to get back to its proper place. This is connected to Aristotle's conception of the cosmos. The cosmos, as Aristotle understood it, consisted of a series of concentric spheres. At the center was the sphere of Earth, outside it was water, beyond that was air, outside that was fire. Those four elements mixed and combined to create the terrestrial world that we see around us. Up above is the fifth element, aether, out of which the planets and the stars are made. The edge of the boundary between the realm of the four elements, the terrestrial realm, and the aether, the celestial realm, is the orbit of the moon. The four elements that make up the terrestrial world that we live in all have a natural place, but of course, the terrestrial world is all mixed up. All kinds of processes move the elements around, and when an element is out of place, it has a natural tendency to return to where it's supposed to be. That natural tendency causes natural motion. Because the natural place of Earth is at the center, Earth always gravitates. It naturally moves downwards to try to be at the center of the cosmos. Water generally gravitates downwards, but if it somehow gets mixed in below the Earth, it will levitate upwards, just as it springs out of springs and creeks out of the ground. Water and fire, from our point of view, generally levitate. They move upwards. This is why the story that is sometimes told about Isaac Newton is not entirely right. It is not that Isaac Newton discovered gravity. Everyone knew about gravity, and the word even was being used prior to Newton's use of it. What Newton postulated, his hypothesis, was of a universal gravitation, a gravitation that didn't reflect just a natural tendency of matter to move to a particular place, but instead a force that operated between all matter. This universal gravitation even operates up in the heavens, between the planets and the sun. By contrast, for Aristotle, the motions of the planets reflected the natural motion that pertains to the aether, the fifth different element. Those motions are circular for Aristotle. All of the heavenly bodies naturally rotate around in circles perfectly and perpetually. In contrast with natural motion, violent motion in Aristotle is caused by contact, where some quantity of motion is passed from one object to another. In the physics that develops out of Aristotle's work, the idea is that velocity is given by a relation between two factors: the strength of the initial force divided by the resistance of the medium that the object is being pushed, usually violently, through. So the medium might be air, or it might be water, or it might be something even more viscous, like oil or tar. In Aristotelian physics, there was always some resistance because there was no empty space. Aristotle thought that empty space was literally impossible. While by modern scientific standards, basically every detail of Aristotle's physics was wrong, and his cosmology, the thing to focus on for the time being is that it represented a useful and, for its time, persuasive account of the nature of the cosmos and of how motion worked. Incorrect science is still science, and Aristotelian thought formed the basis of later developments. Aristotle was one of those giants on whose shoulders Newton stood. That wraps us up for now. In subsequent videos, we will look at the Newtonian and later the Einsteinian paradigms that replaced the Aristotelian one.